morning all, my name is Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about the estimating the degradation function. So what is estimating and how we are estimating the degradation function in the image processing. So the degradation comes in many forms such as motion blur, noise and camera misfocus. In cases like motion blur, it is possible to come up with a very good estimation of the actual blurring function and undo their blur to restore the original image. The mathematical model of the image degradation, that is the observed image g of x comma y equal to f of x comma y into h of x comma y plus e of x comma y. So here g of x comma y is the output image, f of x comma y is the input and h of x comma y is the degradation function. Here E is the noise. So how noise is reducing here? So here degradation comes in many forms such as motion blur and noise and camera misfocus. So these are all like this. These are some three examples are there. Three noises are there. So these are the motion blur, noise and camera misfocus. These are the noises are there. That is some example of degradation. So in the motion blur, it is possible to come up with a very good estimating to actual blurring function. So how much actual blurring is there? How much we are estimating? How much percentage of blurring is there from the original image? We have to estimate first. Then only we have to consider is it noise or not. So sometimes camera also misfocusing. So camera misfocusing is different and motion blurring is different. So sometimes the motion will be blurred, that the image is blurring. So that is a motion blur or camera misfocus. So we have to go to the settings of camera and we have to check once. So that is different. And manually we are going to the blurring the image. That is different. So in that cases, motion blur is possible to come up with very good estimation of the actual blurring function and undo there. Undo means we have to go back and we have to take the proper estimation of that image. So that is one. So how we are estimating the image of the degradation function. The equation is here, the mathematical model for image degradation, that is the observed image, that is g of x comma y equal to f of x comma y into h of x comma y plus e of x comma y. So here g of x comma y is the output and f of x comma y is the input function, h of x comma y is the degradation function plus e of x comma y is the noise, how much percentage. Means here noise is nothing but a motion blur or noises or camera misfocus. So we have to estimating the motion blurring and we have to apply the degradation function and we are reducing the noises. So then we are getting the output as a g of x comma y. So here star, it is denoted as a convolution function. Here we are taking as a convolution function. And f of x comma y is the noiseless image, h of x comma y is the degradation function. So input is a noiseless function, but input is a noiseless, but here noise is occurred. So noise is added to the input image. So f of x comma y is a noiseless image and h of x comma y is a degradation function. Degradation function is applying here to find out or to estimating the noise, how much percentage of noise is there in the original image. So that is a degradation function h of x comma y and we are assuming that it is a linear. Linear means naturally the blurring or the noise is occurred, that is a linear. Non-linear means it is manually we are creating some noises. Okay, not unwantedly means wantedly that was created. So that is the non-linear. Linear means naturally is there. From the original image only we got the noise, that is a linear. So E of x comma y is a noisy image or noisy is there. So E of x comma y is a noisy perturbations of each pixel value. So f of x comma y is equal to input image g of x comma y is equal to output image h of x comma y is a degradation function. Here star is nothing but a convolution. So star is nothing but a in between the f of x comma y into h of x comma y. So f of x comma y into h of x comma y plus e of x comma y. So what is the output function? G of x comma y. So g of x comma y is the output image adding with input image with degradation function h of x comma y plus noise is there. Actually f of x comma y is a noiseless. But what is happening in the meanwhile? The noise is added to the original image. So for the noiseless, noise is happened. So what will there means? Totally it is a noisy image. But what we have to do? H of x comma y is estimating the noise. H of x comma y is estimating the noise or to reduce noise. So here f of x comma y is a noiseless, but here e of x comma y is a noisy is added to the original image. So that is a noisy image. Then degradation function is to finding out the estimating the original image of the noisy, how much percentage of noise. Then we have to using the filters to reduce the noise. Okay, how much percentage is there in the original image depends on the noise of the image. We have to reduce the noise from the original. That is a g of x comma y. So here one example, f of m comma n is a input image. That is the original image. So for the image, I am applying the degradation function. That is a h of m comma n. That means here what is happening? F of m comma n into h of m comma n. F of m comma n into h of n comma n. So star is nothing but the convolution function. Here noise is added. So in the original image noiseless is there, but here noise is added to the original image. That means noisy is there. So g of m comma n is that output image. So this output image is a, if I am using filters, then it is a noiseless. If I am not using filters, so if is it any blurring is there, so it will be finding out how much blurring is there at the output side. So g of m comma n equal to output with noisy. Why? Because input is added to the noise. So noisy image, output is a noisy image. So it is the output is a noisy. So after the output of the noisy image, what do we have to do? So I am using the filter technique. Here I am using filters to reduce noise. So that is a restoration filters. Means output filter is the restored filter. Restoration filter means again f dash of x comma y. So why I am taking f dash of x comma y means here g of x comma y is the output, that is a noisy. So I am reduced the noise or remove the noise from the original image. That is a f dash of x comma y. Here already we know that f of x comma y is the noisy, noiseless. So f dash of x comma y is also noiseless. But meanwhile what is happened means f dash of x comma y equal to g of x comma y equal to f of x comma equal to g of x comma equal to f dash of x comma y. So it is the input image, it is a degradation image, it is the restored output image. So what is first happened means f of x comma y is the input image with noiseless, g of x comma y is a degraded function with noise, f dash of x comma y remove the noise from the g of x comma y, that is a noiseless image that is restored in f of x comma y, that is a f dash of x comma y. So this image is a input is original is a f of m comma n. It is the original input image. So it is a noise image. For the noise image, that is a g of m comma n. So after the noise, we are reducing using the filters. We are reducing the noise. That is a restored filter. That is a restoration of the filters. So it is a estimating the degradation function. So in the image restoration, what are the means? The estimating the degradation function. In the image restoration, first we have to find out how much estimating of the degradation function. There are three principal methods of estimating the degradation function. That is observation, experimentation, mathematical modeling. First one is a observation, experimentation, and mathematical modeling. Observation means noisy or noiseless. Experimentation means apply method. Mathematical model means removing noise. So observation, experimentation, and a mathematical modeling. So these are the estimating the degradation principal functions are the three types. So that is the estimating the degradation function. So the degradation function h, can be estimated by visually looking into a small section of the image containing simple structures with a strong signal contents like what an object and the background. So given a small sub-images gs of x, y, we can manually, that is filtering, remove the degradation in that region with the estimating sub-image and assuming that the additive noise is negligible in such an area with a strong signal content. So that is hs of u comma v equal to gs of u comma v by fs dash of u comma v. So what is here? hs of u comma v is the estimated for such a small subimage. The shape of this degradation function can be used as a estimation of h of u comma v for the entire image. So the estimated output hs of u comma v is the estimated subimage. What is the shape of the image? That is a degradation function. That is a h of u comma v. So gs of u comma v is the degradation function divided by f dash means output image. That is a restored image. So here h of x u comma v is the estimating how much noise is there. Estimating is equal to degradation function with inversely proportional to the restored image. That is a f dash of u comma v. And estimating image experimentation. How we are estimating the experimentation of the image. Suppose if we have an acquisition device producing degradation of the image, we can use the same device to obtain an accurate estimation of the degradation. So the acquisition device means, suppose I am taking one camera or a sensor, it is producing degradation of the image. Producing degradation of the image means we captured the image, but the image may be blur, may be noise, or camera misfocus. So these are the some problems are there from the original image. So that is the acquisition device. It is producing the degradation of the image. Then what we can do? We have to use the same device to obtain an accurate estimation. From the same device, we have to find out accuracy. How much percentage of blurring? How much percentage of noise? So that is the function of estimation of the degradation. That is a g of u comma v. So this can be achieved by applying an impulse, that is a bright dot of an image. The Fourier transform of an impulse is constant. Therefore, h of u comma v equal to g of u comma v by a. So it can be achieved by applying an impulse or bright dot of an input image. The Fourier transform of the impulse input. So what is the impulse constant is h of u comma v equal to g of u comma v by a. So what is here? It is a constant description strength of the impulse function. It is a constant function of the impulse. And the effect of noise of the impulse is negligible. So how much noise is affected to the original image? That is the impulse. It is negligible here. So here h of u comma v is equal to estimated output h of u comma v equal to g of u comma v degraded output with a. A is a constant descriptive strength of the impulse function. So how much and how we are estimating the image experiment. So here some example images are there. Estimating the image experiment. Here I am taking figure A and I am taking some figure B. Figure A is the impulse image. It is the degraded impulse image considering as h of x, y. So it is I am taking as a input image, but some noise is occurred. That is a degraded impulse image. That is a h of x, y. It is a degraded output. Degraded function h of x, y. So the degradation estimation by impulse characterization of an impulse high shown in figure A and image that is a degraded impulse. So the impulse function, the impulse is a figure A and imaged that is a degraded function, imaged degraded impulse, that is a figure B. It is some example of estimating the image experiment in figure A and figure B. Simply we are taking the Fourier transform of the degraded image and after normalization of a constant A, use it as the estimation of the degradation function h of u, v. So the degradation function h of u, v, how we are taking this one means the constant value A is the normal constant value of the degraded image and estimation of the mathematical modeling. Sometimes the environmental coordination that causes the degradation can be modeled by mathematical formulation. The example of atmospheric turbulence can be taken as a h of u, v equal to e power minus k of u square plus v square whole power 5 by 6. It is the value of the degradation function which are using in the atmospheric turbulence of the model. So here k is a constant that depends on the nature of the turbulence. This equation is similar to the Gaussian low pass filter and would reproduce blurring the image according to the value of k. For example, if k equal to, I am taking 0.0025, the model represents severe turbulence if k equal to 0.001. But here k is a constant, depends on the nature of the turbulence. But here I am taking the k value is 0.001. The model represents mild turbulence, and if k equal to 0.00025, the model represents low turbulence. So depends on your k value, the model of the turbulence will be changed. So it is similar to the Gaussian low pass filter. Once a reliable mathematical model is formed, the effect of the degradation can be obtained easily. It is some examples of estimating the degradation function. Figure A, figure B, figure C and figure D. So figure A is a negligible turbulence. Figure B is the severe turbulent of 0.0025. It is a mild turbulent 0.001. It is a low turbulent 0.00025. So here somewhat compared to this one, somewhat it is better. Why? Because here I am taking 0.0025. The lesser value is 0.001 and most lesser value is k equal to 0.00025. It is a most lesser value. So it is a negligible turbulence, severe turbulence and mild turbulence and low turbulence. So these are the some sample examples of estimating the degradation function with the turbulence value. Estimating by mathematical modeling. In some applications, the mathematical model can be derived by treating that the image is blurred by uniform linear motion between the image and the sensor during image acquisition. So the motion blur can be modeled as follows. Let f of x, y is the noiseless image, that is the x and y directions. The time varying function is the x0 of t and y0 of t. The total exposure is obtained by integrating the instantaneous exposure over the time interval during the shutter of the imaging device is open if t is the duration of the exposure of the device. So what is the function? G of x, equal to integral 0 to t f of x minus x0 of t, y minus y0 of t into t. G of u, equal to integral minus infinity to infinity minus infinity to infinity g of x comma y equal to e power minus j 2 pi of ux plus vy into dx dy. Another one is a integral minus infinity to infinity 0 to t f of x minus x naught of t comma y minus y naught of t into dt whole power e power minus j 2 pi ux plus vy into dx into dy. It is estimating the degradation function. These are the references for this topic, estimating the degradation function. So in this we discussed briefly. I will discuss this estimating the degradation function. It is a motion blurring, noise, and camera misfocuses are the examples of degradation or noise image. So we have to estimating with the degradation function how much percent of noise is there. So what is the degradation equation is g of x comma y equal to f of x comma y into h of x comma y plus e of x comma y. Here f of x comma y is the input image, h of x comma y is the degradation function, e of x comma y is a noise function. So star denotes a convolution, f of x comma y is a noiseless image, h of x comma y is a degradation function, and e of x comma y is a noisy perturbation of each pixel value. It is one example for original image with the degradation function f of m comma n into h of m comma n, and the noisy is the nu of m comma n. G of m comma n is a noisy image. So we are using filters to reduce the noise from the g of m comma n. Then after the noiseless image, that is a restoration filter, that is a f dash of x comma y. So how we are estimating? What are the types are there? There are the three types of estimating the degradation function, that is observation, experimentation, and mathematical modeling. So the degradation function h can be estimated with the function g of x comma y, and h of u comma v equal to g of u comma v by f of u comma v. Here h of u comma v is the estimated subimage, h of u comma v is the entire image, and f dash of u comma v is the restored image, that is a f dash of u comma v. So h of u comma equal to g of u comma v by a. So h of u comma v is the Fourier transform of the impulse constant, g of u comma v is the degradation function, and a is the constant of description strength of the impulse function. So these are some examples of impulse image and degraded impulse image. Here the Fourier transform of the function with the turbulence equation, and it is a turbulence values. So mathematically depends on your turbulence values, the k value, then the image should be changed. It is some examples of different turbulence values. First one is a negligence turbulence value, means it is around 0, and next one is a severe turbulence 0.0025, and the figure C is a k equal to 0.0001, somewhat better to the compared to the B value, and from figure C to figure D, low turbulence, that is a 0.00025. It is somewhat better, that is compared to A, B, C, D. D is a less turbulence value. In the figure A, it is a negligible turbulence, that is equal to 0 turbulence value. It is the estimating a degradation function. It is a mathematical function with x and y directions with a time varying motion, that is the x naught of t and y naught of t. It is a equation for output g of x comma y and degraded output g of v comma v. So these are about estimating the degradation function. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.